Hey everyone, welcome back to the video lectures for section 2.3 talking about mathematical modeling. So in this video what we're going to be looking at is one of the main examples of mathematical modeling, or of a model you can make. It's a very simple one, it's a good place to start thinking about these sorts of models and stuff like that. I know it's one that's in the book, but I feel like it is pretty much the standard example of modeling. It'll show up later when we talk about systems. It's a pretty common one that shows up a lot. It's the tank problem. So we're going to talk about the tank problem, set up an example of it, look how the model works, dissect it all into pieces, then solve a problem using it. And that'll be sort of where we go with this video. All right, let's go ahead and jump on into the tank problem. Now, this is not shooting and blowing up things tank. This is like tank of water with salt in it. So we're going to say that we have a 100-gallon water tank with 50 gallons of water in it. So a 100-gallon tank contains 50 gallons of water. And in that water is 5 pounds of salt. And now we're going to have water come in the tank, water flow out of the tank. We're going to analyze the amount of salt in the tank. So water with a salt concentration of 0.25 pounds per gallon. Point to make. With all these mathematical modeling problems, watch your units. Your unit's going to show up and they're going to matter. Just you got to make sure that everything sort of works out in the end, how you set up the problem. And we'll talk about that once we actually write the model. Flows into the tank at a rate of 5 gallons per minute, and water leaves the tank at the same rate. And the tank is well mixed. Now, what well mixed means in this context is that the water coming out of the tank has the same concentration of salt as the water in the actual body of the tank. It's well mixed, so as soon as the water gets in, it gets mixed around and everything works out fine from there. So here's the actual problem. A, find a model for Q of t, the amount of salt in the tank at time t, and B, solve for Q of t. How much salt is in the tank after a long time? So I'm looking for, so T gets bigger and bigger and bigger. What happens to the concentration of salt in the tank? Or the amount of salt in the tank, sorry. All right, there is our problem. I'm going to scroll down a little bit so I can start working on it, but that's what we're trying to do. So here is a picture. If you can draw pictures for problems, pictures are very nice. So we have our tank. And I can't draw, so pictures can be very, very simple. So I have a tank. It has water in it, 50 gallons, and Q of t salt. And into the tank is coming water at a rate of 5 gallons per minute, and salt concentration 0.25 pounds per gallon. That's Q of t is red. And then flowing out of the tank, also 5 gallons per minute. And since it's well mixed, this concentration here is also Q of t. All right, so this picture I've just drawn took all the information from the problem above and threw it into a picture. So I'm going to scroll up again so we can compare the two. So we had 50 gallons of water in the tank. This 5 pounds of salt we have not used yet. This we're still going to use later. Salt concentration of 0.25 flows in at 5 gallons a minute and leaves the tank at the same rate, and the tank is well mixed. So each one of these things went into part of the picture down below. We'll use this part when we actually solve the problem. Or we'll write it down right now just to be concise. We also know that Q of 0 equals 5. And this came from the yellow piece of information, 5 pounds. So Q is in pounds, and that's what we need to sort of put together is then what kind of ODE can we write from this system, from this picture. All right, so how does the amount of salt in the tank change? So dQ of T dt should be what? Well, the amount of salt in the tank should change based on how much comes in versus how much goes out. This should be salt in minus salt out. Now in this case, we're okay just doing this because we're assuming that salt doesn't get created or destroyed inside the tank. So the only way it can enter or leave is by flowing in or by flowing out. So what is the rate of salt flow into the tank? Well, if we look at our in pipe, we know salt flows in 0.25 pounds per gallon times 5 gallons per minute, which will give us the rate at which salt enters the tank in terms of pounds per minute. Right? You cancel the gallons, you get pounds per minute, and that's an okay unit to work with. We can do the same thing for our outside flowing out. We have it's flowing out at Q of T pounds, but this is pounds. This is not pounds per gallon. Right over here, I had pounds per gallon, so I need pounds per gallon. How do I get pounds per gallon? I divide by the 50 gallons in the tank. And then I multiply that by 5 gallons per minute. So again, everything on this side is in pounds per minute, which is what I need. The units have to work out for this to be set up right. So now we can simplify this equation a little bit, and I get that dq dt equals 1.25 pounds per minute minus Q of T divided by 10 pounds per minute. So Q of T, Q of T is pounds per minute. That's what we want it to look like. Good. Okay, now everything's pounds per minute. We're good to go. Q's in pounds, T's in minutes. Okay, so we have this, and we have an initial condition that we had above, Q of 0 equals 5. So this is the answer to part A. This is, we have built a model for this tank problem. All right, make sure you're good with that. We can talk about this more again in class if you want, but make sure you're good with that. Now we want to solve this model. So let's solve this. So how do we solve the ODE? Let's rearrange it to something we might recognize better. So this is Q prime plus 1/10 Q equals 1.25. So now I'm going to drop all the units. I know the units worked. Q is in pounds, T is in minutes, and I know that. So I'm just going to drop all the units. And let's just solve this ODE as it is. So I move the Q over to the left-hand side, and I get that ODE. Now this is a first-order linear constant coefficient ODE. We know how to solve this, right? We multiply by the integrating factor, I'm not going to write out all the steps, but you can sort of follow along. E to the 1 over 10t, which is going to give me this. This side then becomes e to the 1 over 10t times q prime equals 1.25 e to the 1 over 10t. And now I integrate both sides. I get e to the 1 over 10 t q equals 12.5 e to the 1 over 10 t plus a constant. And now I can divide both sides by e to the 1/10 t. Q equals 12.5 plus c e to the minus 1 over 10 t. And finally, we can solve for c because we know that q of 0 equals 12.5 plus c, which we know has to be 5. So c is negative 7.5. And so q of t is 12.5 minus 7.5 e to the minus 1/10 t. And that solved our problem. Now, the last question there asked, what happens at very, very large times? So if t gets really, really big, what happens? Well, e to the minus 1/10 t is going to go to 0, which means q of t is going to approach 12.5 for really, really large t. Is that expected? Yes, it is, and here's why. 12.5 is a quarter of 50 gallons. So at the end, we have a concentration in the tank of 12.5 over 50, which is 0.25 pounds per gallon, which is the exact same rate that the water is flowing into the tank at. So as time goes on, it shouldn't matter what was in the tank to begin with. The tank is going to be replaced effectively by the incoming water because it's all getting flushed, everything else is getting flushed out. So at the end, we would expect to get to 0.25 times 50 or 12.5 pounds of salt in the tank. So there's the worked out example for the tank problem. I hope that made sense. We'll definitely do a lot of these in class, and you've got a couple examples in the book that do things very, very similar to this. You can look at those too for comparison. All right, thanks for watching that, and we'll do one more video about this, doing a couple more examples, not actually solving out problems, just more models in general. And we'll talk about a lot of examples and actually solve problems in class. All right, thanks for watching, and I'll see you in the next one.